This video is going to define the standard deviation and the variance for you. It's also going to teach you how to calculate the standard deviation and the variance. Neither of these two statistics individually is particularly difficult to calculate. It's really more tedious than anything, which is why I want to focus on showing you the calculations and having you learn how to do the calculations outside of class so that whenever we get in class, we can do some more interesting things with these statistics. Now, the standard deviation is defined to be a measure of how far away an observation is from its mean. You can also think of it as how spread out the observations are from one another. If you have a large standard deviation, that means the range of your observations is fairly large. The observations aren't particularly close. If you have a small standard deviation, it means that most of your observations are concentrated close to the mean. The way we calculate the standard deviation in words is by taking the average of the squared standard deviations between each observation and the mean, and then taking the square root. So in other words, we calculate the sample mean, x bar, and we look at each individual observation. So take your first observation, which is x1. Take x1, subtract off the sample mean, x bar, and square that difference. Repeat that for the second observation, x2 minus x bar, that difference squared. Add on the same thing for the third observation, x3 minus x bar squared, and we do this for every single observation in the data set up until our very last observation, x sub n. The last term in that sum is going to be x sub n minus x bar, the quantity squared. After you're done squaring the differences, we divide by n minus 1, the sample size minus 1, and then take the square root of that quotient. Just a note on why we use n minus 1, it turns out we get a better estimate of the standard deviation than just using n. I want to give you a couple facts about the standard deviation. First of all, there are two types of standard deviation. Just like we had two different types of means, we have two different types of standard deviations. We have the population standard deviation, which is denoted by the Greek letter sigma. Population standard deviation is the true standard deviation of the population. It's a parameter, and it's generally unknown. We generally don't know the true spread of a population. The other type of standard deviation that we have is the sample standard deviation. The sample standard deviation is denoted by the lowercase letter s. Sample standard deviation is a statistic, and it's always going to be able to be calculated from the sample of data that you have. Like we mentioned earlier, the smaller standard deviation means that most of your data is going to be concentrated closer to the mean. It means that if you know the mean of your sample, you have a general idea that most of your observations are pretty close to x bar. The standard deviation is always going to be non-negative, and really there are two different reasons that you can think about why this is true. First of all, distance is always positive. The standard deviation is quite literally a measure of how far away an observation is from the mean. Distance is always going to be positive. You can't have a negative distance. So since standard deviation is a measure of distance, standard deviation is always going to be positive. The other reason, really the more mathematical reason, is because the deviations from the mean are all squared. If we take a look at the formula for calculating the standard deviation, up in the numerator, we have x1 minus x bar squared plus x2 minus x bar squared. Each of these differences is going to be squared. So in the worst case scenario, each of these terms is going to be equal to 0. What this means is that your numerator can never be less than 0. So your numerator is non-negative. You take your numerator, you divide it by n minus 1, which is always going to be positive. And then you take the square root of a non-negative number, which is going to give you another non-negative number. So the standard deviation is guaranteed to always be non-negative. In the worst case scenario, you have a standard deviation that's equal to 0. Let's take a look at an example of how we calculate the standard deviation. So let's say that you have 5 finals at the end of the semester, and you want to calculate the standard deviation of the amount of time that you spent studying for your finals. You keep track, and you find out that for one of your finals you spent 10 hours studying, For another one, you felt more confident, you only spent 3 hours studying. Your hardest final, you spent 14 hours studying. And then the last two, 8 and 5 hours respectively. We want to know, what is the sample standard deviation for the number of hours you spent studying? First things first, whenever you want to calculate the sample standard deviation, you need the sample mean. Your sample mean, if you recall, is going to be the sum of your observations, 10 plus 3 plus 14 plus 8 plus 5, divided by the total number of observations, which is 5. The sum in the numerator is 40. 40 divided by 5 gives you 8. So now what we're going to do is we're going to take each individual observation, subtract off the mean, square the difference, add up all of these squared differences, divide by the sample size minus 1, and take the square root. So the first step for calculating your sample standard deviation is going to be working out what's underneath the radical. So your first observation is 10, sample mean is 8, 10 minus 8 squared gives you your first term. 2 squared is going to be 4. Your next term, your next observation is 3. Sample mean is still 8, that doesn't change at all. 3 minus 8 gives you negative 5. Negative 5 squared is your next term. We do the same thing for 14. 14 minus 8 squared. Your next observation is going to be 8. 8 minus 8 squared. And your final observation is 5. 5 minus 8 squared. That finishes off the numerator. In the denominator, we use n minus 1. We have 5 observations altogether. N is equal to 5. 5 minus 1 is going to give you 4. Working out each of these individual terms gives you the following. Your first term in the numerator is 4. Second term is 25. Your third term, 6 squared, gives you 36. The fourth term, since your fourth observation was equal to the sample mean, 8 minus 8 was 0. 0 squared is still 0. And then your final term, 5 minus 8 squared, negative 3 squared, gives you 9. The denominator, 5 minus 1, is equal to 4. We work out what's underneath the radical. Underneath the radical, we get 18.5. And so the square root of 18.5 gives us our sample standard deviation, which is approximately 4.301. I want to also give you an example of how we interpret the standard deviation. So here's our scenario. The weights of NFL players have a mean of 248 pounds and a standard deviation of 24 pounds. We want to know how many standard deviations from the mean is a player who weighs 296 pounds. Here's how we're going to go about this. The difference between the observation and the mean is 296 minus 248, which is 48 pounds. This NFL player is 48 pounds heavier than the mean. A single standard deviation is going to be equal to 24 pounds. And so what we do is we realize that 48 pounds equals 2 standard deviations. 24 plus 24 gives you 48. So 48 pounds is exactly equal to 2 standard deviations. What this means is that 296 pounds is exactly 2 standard deviations above the mean of 248 pounds. The second measure of variability that I want to talk about in this video is called the variance. And the variance, very simply, is just another measure that measures the spread of a set of data. It's directly related to the standard deviation. In fact, it's equal to the square of the standard deviation. So if you find the standard deviation and you square that number, you end up with the variance. Just like the standard deviation, there are 2 types of variances. We have the population variance, which is denoted by sigma squared. This makes sense because the population standard deviation is denoted by sigma. The variance is the standard deviation squared, so the population variance is sigma squared. It should come as no surprise that the sample variance is going to be denoted by s squared. Now just a note about the variance. Typically, we're going to be using the standard deviation whenever we talk about how spread out a set of data is. but occasionally, and this will come up much later on in the course, occasionally it will be necessary to refer to the variance instead of the standard deviation. Let's just take a look at one example of calculating the sample variance to finish this up. We're working with the same example that we had before, the total number of hours that you spend studying for each of your 5 finals at the end of the semester. Same 5 observations, 10, 3, 14, 8, and 5. But instead of calculating the sample standard deviation, what we want to do is calculate the sample variance. If you recall from the earlier example, our sample standard deviation was 4.301. Since we have this direct relationship between the standard deviation and the variance, all we need to do to calculate the sample variance is to take our sample standard deviation and square it. So the sample variance, S squared, is going to be equal to 4.301, the sample standard deviation squared. Working this calculation out gives us 18.5. So the sample variance is equal to 18.5. Now this 18.5 should ring a bell because it turned up in the calculation of our sample standard deviation. We took each observation, subtracted off the sample mean, squared the difference, added up all of these squared differences, and divided by the sample size minus 1. Once we worked through those calculations underneath the radical, what we were left with was 18.5. So this shows you that in order to calculate the sample variance, it goes through the exact same calculation as calculating the sample standard deviation. The only difference is that you don't take the square root of the number that you end up with underneath the radical if you want the sample variance. If you want the sample standard deviation, you do take the square root of what you have underneath the radical. So this concludes the video on calculating the sample standard deviation and the sample variance. Like I said, the calculations are not overly difficult, they're more tedious than anything, but this sets us up so that we can do some more interesting things in class.